Honors Algebra 2, Chapter 3, Section 7. We're going to find determinants, learn what determinants are for matrices, and we're going to use them to solve Cramer's rule, a way of solving systems. So every square matrix, we're talking about square matrices here, we can find a special number called a determinant, and we'll learn kind of some more uses when we do inverses in the coming days. But determinant is a value, a number, and we use it within things. So there's two ways of labeling it. We can say DETA, or we just put an A with the two vertical lines, which looks like absolute value, but when we're talking about matrices, this means determinant. So finding determinants, we're going to look at determinants of 2 by 2s and 3 by 3s. Again, they're only for square matrices, so they have to have the same rows and columns. So we're going to first look at by a 2 by 2. So if I take a 2 by 2, A, B, C, D, to find it, we take the downward diagonal, so A, D, and we multiply those. So A times D. And then you take the upward diagonal and you multiply those. C times B. And you have those two products and you subtract them. And that's how you find the determinant. So the downward diagonal is -4. Downward -1 times 4. Minus the upward diagonal, 3 times 2 is 6. So our determinant here is -10. A 3 by 3 determinant is going to be a little more difficult. To find the determinant of this, to help us out, we'll take the first two columns and we'll repeat this. Repeat them over here. Continue on that pattern. The reason why is when you start looking at the diagonals, the downward diagonals, there's not just this one. We take the diagonal from each of the numbers in the first row. So the first diagonal will be 1, 0, -2. So 1, 0, -2, we write that, which would be 0. We're going to add to that the other downward diagonals. So plus another downward diagonal coming from the middle value 2, 2, 2, 4. We're multiplying those. And then we do it one last time, add the last diagonal. So 3, -1, and 1. So -3. That's just the downward diagonals. We still need to subtract the upward diagonals. So we repeat that same process we just did, but they're from the numbers down here, the upward diagonals. So 4, 0, and 3. That's 0. We're going to add to that the next upward diagonal. 1, 2, 1. So it would be 2. And one last diagonal. 2, -1, 2. Well, that's actually a -2. -2, -1, 2. So then when we're actually evaluating it, we need to find the sum of these, which is 13, minus the sum of these, 6. So we get 7 is the determinant of this 3 by 3 matrix. So those are a little bit confusing, and that's all you do though to find 2 by 2s and 3 by 3s. So finding area of a triangle given 3 points. Area of a triangle is 1/2 base times height is the formula for it. When we're dealing with 3 points, we can use the formula for the determinant of x, y, 1, x, y, 1, and x, y, 1, where these are the different points given to you of the triangle, the vertices of the triangle. And we have to have this column of 1s because determinants only are found of square matrices. So we need to make this a square matrix, we put the 1s in here. But this was how you find the area of a triangle. So if I have a triangle, we plug them in, 3, 4, 1, -1, -2, 1, 4, negative 1, 1. So you need to find the determinant of that 3 by 3 and then cut it in half. And then we should have plus or minus here. Sometimes determinants are a negative value, so if that's the case, we use a negative 1/2 to make the area positive. If the determinant is positive, we use positive 1/2. So you can choose positive, negative to keep our area a positive value. So this is going to be plus or minus 1/2 times. I need to find that value. So the downward diagonal would be negative 6 plus 4, 1, 4, so 16. And I can do this by wrapping around. So I'm going to do 1 times a negative 1 times a negative 1. So plus 1. If you need to rewrite the two columns to find that, you can do that. And we're going to subtract the upward diagonals. So only 4, negative 2, and 1. Plus negative 1, 1, 3. Plus 1, negative 1, 4. And a lot of negative values. So we have 10, or actually 11 minus, this is going to be negative 15. So we're at 26. So we're going to do 1/2 times 26, or 13 units squared will be the area of that triangle. Cramer's rule uses coefficient matrix to solve systems of equations, and this is where we most, I want to say most use. I'm not a huge fan of Cramer's rule for solving systems, but it works, and especially for systems of 3 equations. So if we're given this system right here, we can take this system and turn it into a matrix. Now this matrix, we have the coefficient matrix, and then we have the variables. So the matrix A is the coefficient matrix, A, B, C, D. This is the matrix A. It's the coefficients of all the variables. And if we want to solve for these variables, if we want to find x, x is found by taking this determinant of that coefficient matrix, A, B, C, D, and then in the numerator is another matrix. It's similar to the coefficient matrix, except since we're solving for x, we're going to replace the x coefficients with the solutions. So these get put in place of those. So we're going to have E and F, and then the rest of the matrix stays the same. So we'll have B and D. To find y, same thing. The denominator is always going to be that coefficient matrix. The top, since we're finding y, we want to replace the y values, the y coefficients in the numerator, with the solutions. So the second column here will become EF. The first column stays what it was, the AC, same as the denominator. And you have to find the determinant of these and then divide. And so if you're going to do this for 3 variables, it's some work to find each variable. If you only want to find one and then back substitute, it's pretty quick. And so let's make an example of this. Actually, let's just do one with numbers. An example of this, if I have the matrix or the system 2x minus 3y equals 4, and then if I have 3x plus 5y equals 2, and we'll see what kind of answer we get here. If I want to find x, it's going to be found by doing the matrix. On the bottom is a coefficient, so it's 2, negative 3, 3, 5. The numerator, I replace my x column with the solution, so it's 4, 2. The negative 3, 5 stay the same. So the downward diagonal, 20, minus the upward diagonal, negative 6. So 20 minus negative 6 is 26. Downward diagonal, 10, minus a negative 9, so 19. So it'll be 26/19 is what x is. So even though the answer is really nasty, the Cramer's rule helps us find it efficiently. Y would be the same denominator, 2, 3, negative 3, 5. Our numerator changes. We're going to replace the y column with the solutions. So this numerator is going to be 4 minus 12, negative 8. And 10 minus negative 9 still is 19. So this one cannot be reduced either. So negative 8 19ths would be y. So nasty answers, but Cramer's rule helps us with the math. So one last problem. Let's just have you try this. Find the value of the determinant for the following matrix. So a 3 by 3 matrix. Find the determinant for that, the single value, and then turn that in when you come in. And we're done for the night.